Okay, so picture this.
Yeah.
You're standing on a perfectly still lake, and suddenly a pebble plunges into the water,
Right.
sending ripples spreading outwards.
Okay.
Now imagine those ripples aren't in water, but in the very fabric of space-time itself.
Hmm.
Created not by a pebble, but by the collision of monstrous black holes billions of years ago.
Wow.
Those are gravitational waves.
Yeah.
Ripples in space-time traveling at the speed of light.
Right.
And carrying whispers of some of the most powerful events in the universe.
Really is incredible.
It's like the universe has been playing a silent symphony for eons. We've only just started to listen.
Yeah.
Welcome to Cosmos in a Pod, Space and Astronomy series. Today, we're diving deep into the world of gravitational waves.
Okay.
What they are, how they form,
Right.
how we detect them, and what they can tell us about the universe.
Sounds good.
So these gravitational waves, they're literally ripples in the fabric of space-time.
Yeah. It's pretty mind-bending, right?
Yeah.
It's a
Can you break that down for me a bit?
Yeah.
What does it even mean for space-time to ripple?
Well, think of space-time as the very fabric of the universe, the stage on which all cosmic events play out. According to Einstein's theory of general relativity, massive objects, like stars and planets,
Right.
actually warp this fabric, creating a sort of dent.
Okay.
And when those objects accelerate, like when two black holes spiral toward each other and eventually collide,
Yeah.
those dents become waves that propagate outwards, like ripples on a pond.
Okay, so I'm starting to get the picture.
Good.
But what kinds of events are powerful enough to create these ripples in space-time?
Yeah.
You mentioned black holes colliding, but are there other sources of gravitational waves?
Oh, absolutely. Black hole mergers are definitely some of the most dramatic sources.
Right.
But there are others.
Yeah.
For example, when massive stars die in spectacular supernova explosions, they can also generate gravitational waves.
Okay.
And when two neutron stars, those incredibly dense remnants of collapsed stars,
Right.
spiral towards each other and collide.
Wow.
The resulting cataclysm sends powerful ripples through space-time.
Neutron star collisions. Those sound pretty intense.
Yeah.
I mean, what happens when two objects, the dense, smash into each other?
Well, it's one of the most violent events in the universe.
Really?
Not only do they create gravitational waves, but they also unleash bursts of electromagnetic radiation across the spectrum, from gamma rays to radio waves.
Wow.
It's a cosmic light show accompanied by a symphony of gravitational waves.
Yeah.
And it's in these collisions that many of the heavier elements in the universe are forged, including gold and platinum.
Wait, so the gold in my wedding ring was actually created in a neutron star collision billions of years ago.
It is, isn't it?
That's amazing.
It gives a whole new meaning to the phrase cosmic connection.
Yeah.
And these are just a few examples.
Okay.
There are other potential sources of gravitational waves, like pulsars, rapidly spinning neutron stars.
Yeah.
And even the Big Bang itself would have created a background hum of gravitational waves. If we could detect those primordial waves, it would be like listening to the echo of the universe's birth.
Wow. So we've got all these incredible events happening in the universe,
Yeah.
taking space-time and sending out these ripples. But if they're so faint, how in the world do we even detect them?
Right, that's the question.
I mean, we're talking about measuring changes smaller than a fraction of an atom's width, right? So
Right. It's a truly remarkable feat of engineering and scientific ingenuity.
Yeah.
The instruments we use to detect these minute changes are called laser interferometers.
Okay.
LIGO, the Laser Interferometer Gravitational Wave Observatory, is the most famous example.
Right.
It uses lasers and mirrors to measure the stretching and compressing of space
Right.
caused by passing gravitational waves.
So how does that work?
Well,
I mean, how can a laser measure something as subtle as a ripple in space-time?
imagine a giant L shape with arms that are kilometers long.
Okay.
At the end of each arm is a highly polished mirror.
Right.
Lasers are constantly bouncing back and forth between these mirrors.
Mm-hmm.
When a gravitational wave passes through, it stretches one arm of the L while compressing the other.
Oh.
The lasers pick up this tiny difference in distance, and that's how we detect the wave.
So it's like the laser is acting as a super sensitive ruler, measuring the changing distance between the mirrors.
That's a great way to put it.
Okay.
And it's not just LIGO.
Right.
There are other gravitational wave detectors around the world, like
Yeah.
Virgo in Italy and Ka-ra in Japan.
Okay.
By working together, these observatories can pinpoint the location of gravitational wave sources in the sky and gather even more data about these events.
Wow, this is just incredible. I'm starting to see why this is such a groundbreaking field.
It really is. It's like we've suddenly been given a new sense,
Uh-huh.
a new way to perceive the universe, beyond just light and other forms of electromagnetic radiation.
Yeah.
And with each detection, we're learning more about the most extreme environments in the cosmos.
Speaking of which, let's talk about what we can actually learn from these gravitational waves.
Okay.
What kind of information are they carrying about these mind-boggling events?
Well, first of all, gravitational waves allow us to see events that are otherwise invisible to traditional telescopes, like the mergers of black holes.
Right.
These are objects so dense that not even light can escape their gravitational pull.
Okay.
But with gravitational waves, we can hear these collisions, these cosmic dances, revealing their secrets.
That's fascinating. We're getting a glimpse into regions of the universe that were previously hidden from our view.
Right.
What else can we learn?
Well, for example, by analyzing the gravitational wave signal, we can determine the masses of the black holes that collided, their distance from Earth, their spins, and even the orientation of their orbits. It's like we're reconstructing the crime scene, piecing together the details of this cosmic collision billions of years ago.
So each gravitational wave is like a cosmic fingerprint, unique to the event that created it.
That's a great analogy. And it's not just about black holes.
Yeah.
Remember those neutron-star collisions we talked about?
Yeah.
Gravitational waves from those events can tell us about the properties of neutron stars,
Right.
which are some of the densest objects in the universe.
Okay, so we're learning about black holes, neutron stars.
Yeah.
But what about the bigger picture? Can gravitational waves tell us anything about the universe as a whole?
Absolutely. For example, we can use gravitational waves to measure cosmic distances,
Okay.
which helps us refine our understanding of the universe's expansion and evolution.
Right.
And remember those primordial gravitational waves from the Big Bang?
Yeah.
If we could detect those, it would be like looking back in time to the very beginning of the universe, revealing secrets about its earliest moments.
Wow. It sounds like gravitational wave astronomy has the potential to revolutionize our understanding of the cosmos.
It really does.
Okay.
And this is just the beginning.
Right.
As our technology improves, we'll be able to detect even fainter gravitational waves, revealing even more secrets about the universe.
I'm already hooked. But before we dive into the future of this field,
Yeah.
I want to go back to the basics for a moment.
Okay.
Can you explain in a bit more detail how gravitational waves actually work? What makes them a wave?
Sure. Gravitational waves are transverse waves, which means that they stretch and compress space-time in directions perpendicular to their direction of travel.
Okay.
Think of a wave moving across the surface of water.
Right.
The water itself doesn't move forward with the wave. Instead, it moves up and down, perpendicular to the direction the wave is traveling.
Okay, I'm picturing that.
Good.
But how do we actually measure this stretching and compressing of space-time?
Right.
It must be incredibly subtle.
It is. And that's where those incredibly sensitive laser interferometers come in.
Right.
They're designed to measure this strain, that is, the amount of stretching or compressing caused by the wave.
Strain measurement, so it's essentially how much space itself is distorted by the passing gravitational wave?
Exactly.
Okay.
And it's an incredibly small effect.
Yeah.
We're talking about changes in distance that are far smaller than the width of an atom.
That's mind-boggling.
Yeah.
I can't even imagine trying to measure something that small.
It's a testament to human ingenuity and persistence that we've managed to develop instruments capable of such incredible precision.
So by measuring the strain, we can actually learn about the properties of the objects that created the waves.
Precisely.
Okay.
For example, the amount of strain tells us about the mass of the objects involved in the event. The bigger the mass, the stronger the gravitational waves,
Right.
and the greater the strain.
Okay, I'm starting to see how this all fits together. We're essentially listening to the universe's gravitational symphony
Yes.
and using those sounds to decipher the secrets of some of the most powerful events in the cosmos.
That's a beautiful way to put it. And the information we can glean from these sounds is truly astounding.
Yeah, that's amazing.
For example, did you know that when two black holes collide, The energy released in gravitational waves can exceed the combined energy output of all the stars in the observable universe during the event.
Whoa.
Yeah.
That's impossible to even wrap my head around.
It really is mind-boggling.
Yeah.
But that's the beauty of gravitational wave astronomy. It's constantly challenging our understanding of the universe
Right.
and pushing the boundaries of what we thought was possible.
Well, this has been absolutely fascinating.
Yeah.
I'm already eager to hear more about what the future holds for this incredible field.
Well, get ready, because we're just getting started. The future of gravitational wave astronomy is incredibly exciting.
Yeah.
We're on the cusp of a new era of discovery, and it's only going to get more incredible from here.
Okay, I'm all ears.
Okay.
What kind of advancements are on the horizon? What
Yeah.
are scientists working on that has you so excited?
Well, for one thing, we're building even more sensitive detectors. LISA, the Laser Interferometer Space Antenna, will be a space-based observatory, free from the limitations of Earth-based detectors.
Space-based?
Yeah,
Wow, that's taking things to a whole new level.
it is.
What will LISA be able to detect that LIGO can't?
LISA will be sensitive to lower frequency gravitational waves,
Okay.
which means it'll be able to detect events involving even more massive objects,
Right.
like the mergers of supermassive black holes at the centers of galaxies.
Mhm.
Those events are too massive and too slow for LIGO to pick up.
So we'll be able to witness the cosmic ballet of
Yeah.
giants, black holes, millions or even billions of times the mass of our sun,
Yeah,
spiraling towards each other and colliding.
exactly.
Wow.
It'll be like opening another window onto the universe, revealing a whole new realm of cosmic phenomena. And with each detection, we'll learn more about the evolution of galaxies, the formation of the large-scale structure of the universe,
Right.
and the nature of gravity itself.
I can see why you're excited. It's
Yeah.
like we're moving from listening to whispers to hearing the full roar of the universe.
Yeah, it is.
But it's not just about building bigger and better detectors, is it? What other breakthroughs are on the horizon?
Another exciting development is multi-messenger astronomy,
Hmm.
where we combine gravitational wave observations with observations from traditional telescopes
Right.
that detect light, radio waves, X-rays,
Ah.
and other forms of electromagnetic radiation.
So instead of just hearing the universe with gravitational waves, we'll be able to see it too, getting a much more complete picture of these cosmic events.
Exactly. Remember those neutron-star collisions that create gold and platinum?
Yeah.
Well, when those events happen,
Huh.
they not only emit gravitational waves, but they also produce a burst of light and other electromagnetic radiation.
So by combining those observations, we could pinpoint the location of the collision,
Yes.
see the afterglow of the explosion, and analyze the light to learn even more about the processes that created those heavy elements.
Precisely.
Okay.
It's like having multiple witnesses to a cosmic crime scene,
Right.
each providing a different piece of the puzzle.
Hmm.
And by putting those pieces together,
Yeah.
we can build a much richer and more nuanced understanding of these incredible events.
It's like we're moving from black and white silent films to full-color IMAX movies of the universe.
Exactly.
But with all these new discoveries, there must still be some big questions that are keeping scientists up at night.
Uh-huh.
What are the big mysteries that gravitational wave astronomy is still trying to solve?
Oh, there are plenty. One of the biggest ones is the nature of black hole singularities.
Okay.
These are the points at the center of black holes,
Right.
where, according to our current understanding of physics, density and gravity become infinite. It's a region where our current laws of physics break down.
So basically a point where everything we know about the universe goes haywire.
Pretty much. We don't really know what happens at a singularity.
Right.
Do the laws of physics as we know them still apply? Do they break down completely? Are there new laws of physics that we haven't even discovered yet that govern these extreme environments?
It's like staring into the abyss of the unknown.
Exactly, and that's what makes it so fascinating.
Yeah.
Gravitational waves might provide clues to help us understand these enigmatic singularities. They might also help us unlock secrets about the very first moments of the universe.
You're talking about those primordial gravitational waves from the Big Bang?
Yes. If we could detect them, it would be like listening to the echo of the universe's birth.
Wow.
A signal from a time when the universe was just a fraction of a second old.
That's amazing.
Imagine the secrets those waves could tell us about the origins of everything we see around us.
It's mind-blowing to think that we might one day be able to listen to the very first tremors of the universe. What other mysteries are out there?
Well, On a more practical level, we're still trying to understand how often black hole and neutron star mergers actually happen.
Hmm.
We've detected a handful of events so far,
Right.
but that's just a tiny fraction of what's likely happening out there in the vastness of space.
So it's not just about detecting these events, it's about understanding their frequency and distribution throughout the universe.
Exactly.
Okay.
Knowing how often these mergers occur is crucial for building accurate models of the universe's evolution.
Right.
It can also help us understand the formation and distribution of heavy elements like gold and platinum.
So even with all the incredible discoveries we've made so far,
Yeah,
we're still just scratching the surface of what gravitational wave astronomy can teach us.
absolutely. It's a young field, but it's already revolutionizing our understanding of the universe.
Okay.
And with each new discovery, we're realizing just how much more there is to learn.
I have to admit, I'm a little bit lost on how we actually extract all this information from these waves. How do we go from measuring a tiny wobble in a mirror to understanding the properties of a black hole billions of light years away?
It's a complex process, but here's the basic idea. When a gravitational wave passes through LIGO,
Uh-huh.
it stretches one arm of the interferometer while compressing the other.
Right.
The lasers bouncing back and forth between the mirrors pick up this tiny difference in length.
Okay.
And that signal is what we analyze.
So the pattern of stretching and compressing, that's the key.
Exactly. That pattern, known as the waveform,
Okay.
encodes all sorts of information about the source of the waves.
Right.
By comparing the observed waveform to theoretical models generated by supercomputers,
Uh-huh.
we can determine the masses of the objects involved in the collision,
Okay.
their distance from Earth, their spins, and even the orientation of their orbits.
It's like a cosmic Rosetta Stone, allowing us to decode the secrets
Yeah.
hidden within these ripples of spacetime.
That's a great analogy.
Okay.
And with each detection, we're refining our ability to read these cosmic messages, unlocking deeper and deeper layers of understanding about the universe.
This is also fascinating, but I'm curious, with all this talk about black holes and neutron stars, are there any gravitational waves that we could potentially detect from less extreme events?
That's a great question. While the most powerful gravitational waves come from these cataclysmic events, there are also fainter waves generated by less dramatic objects.
Okay.
For example, pulsars.
Right.
Those rapidly spinning neutron stars we mentioned earlier emit continuous gravitational waves, though much weaker than those from mergers.
So it's like a constant hum compared to a sudden crash.
Exactly.
Okay.
And as our detectors become more sensitive, we
Yeah.
might be able to detect these continuous waves from pulsars,
Right.
providing us with another tool to study these fascinating objects.
It seems like the possibilities are truly endless.
They are.
I can't wait to see what the future holds for this field.
Yeah.
But before we wrap up,
Okay.
I have one final question. With all this focus on the scientific discoveries, do you ever just step back and marvel at the sheer wonder of it all? The fact that we can detect these ripples in space-time, these echoes from the most distant reaches of the cosmos.
Oh, absolutely. It's one of the things that drew me to this field in the first place.
Hmm.
The idea that we can listen to the universe, that we can peer into the heart of black holes and witness the birth of heavy elements.
Yeah.
It's both humbling and exhilarating.
It really is.
Yeah.
It's a reminder that we're part of something much bigger than ourselves, a cosmic symphony that's been playing out for billions of years.
And we're just beginning to understand the music.
Yeah, it really is awe-inspiring to think about all the secrets the universe is still holding, just waiting to be discovered.
Absolutely.
And it sounds like gravitational wave astronomy is going to play a major role in unlocking those secrets.
Without a doubt, it's a field that's bursting with potential.
Right.
And we're only just beginning to explore the possibilities.
Before we wrap up, I wanted to touch on something you mentioned earlier.
Sure.
The idea of using gravitational waves to test Einstein's theory of general relativity.
Right.
Can you elaborate on that a bit?
Sure. Einstein's theory of general relativity has been incredibly successful
Yeah.
in explaining the behavior of gravity on large scales, from the orbits of planets to the bending of light around massive objects.
Right.
But it's never been tested in the most extreme environments,
Okay.
like those found near black holes and neutron stars.
So gravitational waves offer a way to test Einstein's theory in these extreme conditions
Yeah,
where gravity is pushed to its limits.
exactly. By studying the gravitational waves emitted from these events, we can see if they behave as predicted by general relativity,
Right.
or if there are deviations
Okay.
that might point to new physics, new theories of gravity that we haven't even conceived of yet.
So it's not just about confirming what we already know.
Right.
It's also about potentially discovering something entirely new.
Yeah.
Something that could revolutionize our understanding of the universe.
Precisely. Every time we detect a new gravitational wave signal, we're essentially conducting an experiment on gravity itself.
Right.
Probing its nature in ways that were never before possible.
Wow, that's incredible. It's like we're using the universe as a giant laboratory
Yeah.
to test our most fundamental theories.
Exactly.
And who knows what we'll find? Perhaps general relativity will hold up perfectly,
Right.
even in these extreme environments.
Yeah.
Or perhaps we'll find subtle deviations that hint at something new, something that will force us to rethink our understanding of gravity and the universe as a whole.
It's possible.
Either way, it's bound to be a groundbreaking discovery.
Yeah, I think so.
This has been an absolutely mind-blowing deep dive into the world of gravitational waves.
It has been.
I feel like I've only just begun to grasp the immensity of what we're talking about, but it's been a truly fascinating journey.
It's been my pleasure to share this journey with you.
Well, thank you.
It's a privilege to be part of the scientific revolution, and I can't wait to see what the future holds for gravitational wave astronomy.
Yeah.
Who knows what secrets the universe will whisper to us next?
I'm on the edge of my seat waiting to find out. And to our listeners, we hope you found this exploration of gravitational waves as captivating as we did.
I hope so.
If you'd like to delve deeper into the mysteries of the cosmos, be sure to follow and subscribe to Cosmos in a Pod and our YouTube channel for more deep dives into the wonders of the universe.
Sounds good.
Until next time, keep looking up and keep wondering.